Self-inductance and mutual inductance are going to be the topics of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson, we'll start by talking about self-inductance and the nature of this induced EMF, if you will, that a wire causes on itself by its own changing current. And then we'll move on to talking about mutual inductance, where the changing current in one coil causes an induced EMF in a second coil. And then we'll finish this lesson off talking about transformers, a special application of both. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So let's start this lesson off by talking about self-inductance. It's going to be related and almost analogous to the back EMF we talked about with motors in the last lesson. Now, if you look at that word inductance and you think that it's related to like induction and induced EMF, well, you'd be exactly right. So if you recall, Faraday's law gave us kind of the EMF of that induced EMF, if you will, caused by a changing magnetic flux over time. And we talked about that changing magnetic flux could be due to a change in the strength of the magnetic field, a change in the area of the loop, or a change of the angle theta between the magnetic field and the plane of the loop. So in this case, we want to focus just on a change in the strength of the magnetic field, but a very specific magnetic field. So in the last chapter, we learned that a magnetic field is caused by a current in a wire, and that's where we're going to focus. So that magnetic field, if we're going to get a change in that magnetic field, then it's going to be caused by a change in the current. And that changing current is going to be the focus of this entire lesson in talking about both self-inductance and mutual inductance. So let's say we take a look at a simple circuit here with a battery and a resistor and a switch. And we learned with Ohm's law that we can calculate the current in this circuit if we know the value of the EMF and the resistance. Say this was a 12-volt battery and a 2-ohm resistor. We could calculate very easily with Ohm's law that it's a 6-amp current flowing through the circuit. What we didn't tell you, though, is that it takes a little bit of time to get up to that 6 amps. The current's going to grow from, once we close the switch anyways, it's going to grow from 0 up to 6 amps and then steadily hit that 6 amps. So if we look at the graph of the current versus time, it looks something like this, where that maximum current we asymptotically approach here is equal to that ratio of either epsilon over r, delta v over r, same diff according to Ohm's law. But we don't hit there instantaneously. And so once we reach that max current, we're going to stay constantly having that current. And if we have a constant current, we'll end up with a constant magnetic field. If we have a constant magnetic field, then we're not going to have a changing magnetic flux, and there'll be no induced EMF. But up until we reach that point, the current is changing. And because the current's changing, the strength of the magnetic field's changing. Because the strength of the magnetic field's changing, there's a change in magnetic flux over time, and there's an induced EMF. This is what we're going to term self-inductance. So it's not because of something else, it's due to what's going on in this circuit that's then affecting this same circuit. So that's the idea behind self-inductance here. All right, so it turns out we've got a simple formula here for this self-inductance. So I want to see where that kind of comes from with regard to Faraday's law. Now again, we might talk about this change in the magnetic flux is proportional because it's responsible, or at least what's responsible for it is a change in the strength of the magnetic field. So, but that's proportional to the change in the current because it's the current that's causing it. So they're all proportional. So the magnetic flux is proportional to the magnetic field is proportional to the current, and the changes in each are all proportional as well. And so in this case, we want to kind of focus on getting from here to here. So instead of looking at the induced EMF being related to a change in magnetic flux, we're actually relating it all the way back to a change in the current instead with our self-inductance. And so they're proportional, and the proportionality constant we add L here is called the inductance. So in this case, the self-inductance. And it turns out it has units of henries, capital H. And if we look at what a henry ultimately is, we can kind of rearrange and solve for it. So L here is going to equal E times delta T over delta I, and you can see why a henry is equal to a volt second over, let's get that delta I over there. My bad. Over delta I, there we go, over an amp. So volt second over amps. All right, so that's what a henry is, and that is the SI unit for inductance as well. So another new unit to file away. Now it turns out we can come up with another expression for L here, besides this one right here, and the idea is that this induced EMF here and the one given by Faraday's law, it's exactly the same value. So just expressed in terms of different terms. Instead of expressed in terms of the changing magnetic flux, it's expressed in terms of the changing current. And if we set those equal to each other, and so in this case negative L delta I over delta T is going to equal negative N change in magnetic flux over the change in time. So here the change in times are going to cancel. So, but we can then, and the negative signs, truth be told, we'll get rid of those too. We'll just make those positives. And then solving for L, we're going to get change, let's get that N back in there. So N times the change in the magnetic flux over the change in the current. All right, now if we look at these changes, again, these changes, it turns out the ratio of the changes is the same ratio as actually the magnetic flux itself and the current itself. And again, the reason for this is that not only was the change in the magnetic flux due to the change in the current, but the magnetic flux is due to the current as well. And again, these are proportional just like these are proportional, and the ratios are exactly the same ratio as well. And so now we've got another expression for this value for the inductance as well. Now, in principle, the value of the inductance for a simply designed inductor, so can kind of be related to the geometric parameters of that inductor and stuff like that, but normally we just kind of plug them into a circuit and kind of just experimentally determine what the value of the inductance is going to be. Now here I've presented this idea of self-inductance in the context of a DC circuit, a direct current circuit, but in an alternating current circuit where the current is alternating all the time and therefore always changing. Well, if you always have a changing current, you're always going to have some sort of induced EMF. So, but it's not always changing by the same amount and stuff like that. So you also have this EMF that's going to be alternating, this induced EMF alternating in an AC circuit as well, which we'll definitely not discuss too much now, but we will get into a little bit more in the future. So now we'll move on to talking about mutual inductance. And mutual inductance usually comes up in the context of alternating current, and so that's the context I'm going to present it in. So, and this is going to involve two circuits now. Now with self-inductance, we saw that a changing current in a circuit leads to an induced EMF that opposes that change in current in the same circuit. Well, what we're going to see now is that the changing current in this circuit over here is going to lead to an induced EMF. So over here, that's going to oppose the change in current in the original circuit. So the second circuit over here, there's no EMF source over here at all, but it will have an induced EMF due to what's going on over here. And that shouldn't be super surprising. If you recall, so Faraday's law relates this induced EMF back to a change in magnetic flux. So, and this is the symbol for alternating current right here. So because the current is changing over here, so that changing current, and I'm going to call it change in the current in I1 here, because I'm going to call this I1 versus I2. But the changing current over here, that's going to be proportional to the change in the strength of the magnetic field. And that change in the strength of the magnetic field is also in turn going to be proportional to the change in magnetic flux as well. So if we kind of take a look at what's going on here, so let's say at some instant here we've got a current pointing in this direction. So we can kind of put our fingers in the direction of the loops and look at, there's a magnetic field running right down the middle at that particular instant. If you recall with alternating current, the polarity changes and the current might slosh the other direction and things of this sort. But right at this instant where the current is flowing in that direction, so there is a magnetic field pointing right down the middle of the coil, if you will. And I say right down, I shouldn't say right down, it's really pointing to the left. So I didn't use it right in that context, but it's pointing to the left down the middle of that coil. Well, if we wrap it around some sort of magnetic material, like a ferromagnetic material, and an iron core is pretty common, and wrap the second one around here, well, being very magnetic, so it can magnetize this whole region, if you will. And so this magnetic field is also going to be felt over here. And so the changing current causes a changing magnetic field and a changing magnetic flux. That's again experienced by the second one. Now in this case, I told you that the current pointed this way, and ultimately we determined that a magnetic field points that way as well. Well, the key is I don't really know what direction the magnetic field points. I need to know what direction the change in the magnetic flux points. So if the current at this point points to the left and it's increasing is going to be the key. So then I can say that not only does the magnetic field and magnetic flux point this direction to the left, but the change in the magnetic flux also points to the left. So then what we'll find out over here is that the induced EMF and the induced current is going to lead to a changing magnetic flux that's going to have to point in the opposite direction to the right. And so we'd find out that it's going to go around this way instead. And we'd find out that this current through this one at this exact instant, so is going to flow in that direction. That'll be of interest here in a little bit. We've actually solved half of the question of interest that we'll talk about here shortly. Okay, so there's Faraday's law. Well, again, in relating the change in the magnetic flux, we actually want to relate this induced EMF to a change in the current, but not a change in the current in the same circuit, but a change back in the current of the original circuit that's kind of causing this mutual inductance. So, and that's what this lovely formula does. So here I've got it, E here, the induced EMF, and we might even label this better and say that the induced EMF in the second coil is related, it kind of is opposing the change in the current back in the first coil. And for such reasons, with mutual inductance, we often designate these two coils. So the one with the alternating current here, so with the, and it doesn't have to be alternating, but it usually will be, that is the primary coil. So, and the one experiencing this mutual inductance is going to be the secondary coil. It has no EMF source of its own, but is experiencing induced EMF due to the proximity of the first coil, the primary coil. So there's our names. And so here, the induced EMF in the secondary coil, so is due to a change in the current in the first, in the primary coil. So, and it's opposing that change according to Lenz's law, which is kind of what we used to see that direction. So with Faraday's law, we kind of looked at, opposing the change in the magnetic flux, whereas here we're looking at opposing the change in the current. So in the next lesson, when we deal with RL circuits, we'll kind of revisit that kind of property of inductors in which they're opposing the change in the current. Now the induced EMF, as shown by Faraday's law, and the induced EMF here according to our formula for mutual inductance, again, those are the same EMFs, and we can set them equal to each other just like we did with self-inductance. And so in this case, negative M delta I over delta T is going to equal negative N, change in magnetic flux, over change in time. And once again, change in times are going to cancel, the negative signs are going to cancel. And if we solve and rearrange this for M, I'll put that here. So M here is going to equal so N times the change in the magnetic flux over the change in the current. And again, these changes are proportional in the same way that the original properties are proportional as well. So we can write it like so. So completely analogous to what we did with the equations involving self-inductance. And that kind of makes us ready to proceed on with the first problem of interest here, dealing with mutual inductance. So the problem here is going to include this lovely diagram with one key difference. So labeled on the diagram. So, well, one, the direction of the current here, and this one wasn't labeled. So, but this resistor was labeled as having a resistance of 2.0 ohms. All right. Question says, at the instant shown, the current in the primary coil on the left is increasing from 2.0 amps to 12 amps in 0.20 seconds in the direction shown. If the mutual inductance is 240 millihenries, then how much current is passing through the resistor in the secondary coil at this instant? In which direction, left or right? All right, so we got some work ahead of us, but we want to find out ultimately how much current's passing through this. And we're going to use Ohm's law to do that, but to do that, we need to know the induced EMF in this as well. So, and once we get the induced EMF, we can then use Ohm's law, delta V equals IR, and the value of the resistance provided to get the current passing through it. And then once again, we can use Lenz's law to figure out what the direction is, even though we kind of already figured it out. Okay, so in this case, going back to our lovely definition here, we can relate this induced EMF to the value M, which was provided, 240 millihenries, the change in the current over the change in time, and that's exactly what we're going to do here for this calculation. So M here again, 240 millihenries, and let's put that in henries right off the bat. So that's going to be 0.24 henries. So, and then change in current over the change in time. In this case, we're just going to do final minus initial. So, and the question said, going from 2.0 amps to 12 amps, so that's going to be final minus initial, all over 0.20 seconds. All right, so from here we can do some plugging and chugging. So 12 minus 2 is 10, and 10 divided by 0.2. You might recall that 0.2 is the same thing as 1/5, and dividing by 1/5 is the same thing as multiplying by 5. And so in this case, 10, so multiplied by 5 is going to be 50. So, and then times 0.24. Well, multiplying by 50 is the same thing as multiplying by 100 and then dividing by 2, which is kind of how I like to do this. But obviously, you could also let your calculator do all the heavy lifting for you in this case. All right, so once again, so we've got 50 times 0.24. Well, I'm going to multiply this by 100, which gets me 24, and then divide by 2 instead of multiplying by 50. So that's going to get me an EMF here of negative 12 volts. And again, the negative sign is just direction. It's just telling me that it's opposing the change in the current and the change in the magnetic flux, either according to Faraday's law or according to our new EMF, induced EMF of mutual inductance here. All right, but that magnitude is 12 volts, and then go into Ohm's law. So we can rearrange delta V equals IR to solve for the current. Delta V over R, which in this case is the 12 volts over the 2 ohms. So with 2 sig figs is going to get me 6.0 amps. So there's our magnitude. And notice I dropped the negative. The negative again just means it's opposing our change in magnetic flux and our change in current. But again, we use Lenz's law to actually figure out the direction. And going through it one more time here. So in this coil right here, the current points to the left here as it goes through this coil, so which is going to cause a magnetic field to point to the left using Lenz's law. So, or I should say using the right-hand rule. So, and not only does the field and the flux point to the left, but because it's increasing, that means the change also points to the left. That's what we need to oppose. So whatever direction the current is over here, it needs to have a magnetic flux as a result of the induction that points to the right. And I'll curl my fingers around the direction of that coil. My thumb points to the right. So as we go around this way, and again, that's how we determined that the current was flowing in this direction right here. So it's going from left to right, in this case, through the resistor. So let's take a look at a special application of mutual inductance, and that is going to be the transformer. So the transformer is just a special application of mutual inductance. It's still going to involve a primary coil and a secondary coil wrapped around some sort of common magnetic core like an iron core, things of a sort. It's a special application of AC circuits, alternating current circuits, as symbolized here in the primary coil. And truth be told, these are absolutely essential to the proper functioning of our electrical grid. You might look at the power lines in your neighborhood, and those might have 20,000 volt potential difference across them. Well, the electricity at your house coming off your electrical panel is just 120 volts. So how do we get from 20,000 volts to 120 volts? Well, we use a transformer. And in this case, we would call it a step-down transformer. So because we're going from a higher potential difference to a lower potential difference. So, and it turns out from, the power lines to your house is not the only place you might see these. If you want to recharge batteries, so for recharging AA batteries, I think it might only require 2 or 3 volts for potential difference. Well, again, at your house, what's coming in, coming in at the electrical panel and coming to the plugs at your walls is 120 volts. So you'd have to step it down even further. And so typically those recharging devices have a transformer built into them as well. The transformers here, their job is really to change the potential difference in an AC circuit, in the grid, either stepping it up or stepping it down as needed. Now, if we go back and take a look at Faraday's law here, so Faraday's law shows that the induced EMF is related to this change in the magnetic flux over the change in time. Well, again, in our AC circuit here, we've got an alternating current, a continuously changing current, and a continuously changing current is going to give us a changing magnetic flux over time. So, and because the coils here are wrapped around the same common magnetic core as the coils in the secondary circuit are, so the secondary circuit's going to experience exactly the same change in magnetic flux over time. These are going to be equal. Now, I've color-coded them, but we might label them as change in magnetic flux 1 and change in magnetic flux 2. And if I go back to Faraday's law, we can come up with an expression for the change in the magnetic flux. So here, the change in the magnetic flux over time is going to equal negative EMF over N. Let's get a better equal sign there. All right, we can now substitute that back in over here and say that the negative EMF in the primary coil relative to the number of turns of the primary coil is going to be equal to the negative of the EMF in the secondary coil relative to the number of turns in the secondary coil. Well, we're going to drop those negatives. They just cancel each other out. So we get this lovely expression. Sometimes we'll rearrange this just a little bit, and we'll get E1 over E2, or epsilon 1 over epsilon 2, or EMF 1 over EMF 2 equals to N1 over N2. And ultimately what this means is just that the EMF in the primary and secondary coils is directly proportional to how many turns there are for those particular coils. So if you want a step-down transformer, all you got to do is make sure that the secondary coil has fewer turns than the primary coil. If you want a step-up transformer, then you just got to make sure that the secondary coil has more turns than the primary coil. So if you want, in a step-down transformer, if you want half the voltage, well, this expression just means you need half as many turns in the secondary coil as the primary coil. If you're in a step-up transformer, you want 10 times the voltage, well, then you just need 10 times as many turns in the secondary coil as in the primary coil. That's what this equation means. Now, it turns out that the power in the primary and secondary coils is going to be the same as well. Now, in practice, a little bit might be lost to heat or something, but in principle, we're just going to say that they're equal. Well, you might recall that power was equal to delta VI. And so here we can come up with another expression, delta V1 I1 equals delta V2 I2. So another relevant expression for transformers, but ultimately what this means is that your potential difference and your current are inversely proportional. If I double the potential difference in the primary coil, I'm going to have to cut the current in half to maintain the equality. So if the potential differences are proportional to the number of turns here, but the potential differences are inversely proportional to the currents, well, then the currents are also going to be inversely proportional to the number of turns. We can come up with another expression there and express it that way as well. And we could say that, so current 1 relative to current 2 is not going to equal N1 over N2, but it's actually going to equal N2 over N1. There's an inverse proportionality going on there. And now we're ready to do some plugging and chugging regarding transformers. And question of interest says the primary coil of a transformer consisting of 500 turns has an EMF of 1200 volts and a current of 1.0 amps. If the secondary coil has 50 turns, then what is its EMF and current? All right, so in this case, we're going from N equals 500 down to N equals 50. So a reduction in the number of turns by a factor of 10. Now, if again you understand how a transformer works, you don't have to use these equations. The numbers are pretty nice here. So in this case, a 10-fold reduction in the number of turns is going to lead to a 10-fold reduction in the potential difference, the EMF, but a 10-fold increase in the current. So, and those calculations are easy enough. So if we're going from 1200 volts on this side, a 10-fold reduction would take us down to 120 volts on the other side. Similarly with the currents, if we've got a current on this side initially of 1.0 amps, in this case the reduction in the number of turns leads to an increase in the current. And a 10-fold reduction in turns, a 10-fold increase in the current. It's now going to be 10.0 amps instead. Cool, and again, you could get that using these equations. It would lead you to exactly the same numbers, but I made them nice so we could at least see in principle that again, the change in the number of turns is proportional to the change in the EMF and inversely proportional to the change in the current. If you found this lesson helpful, consider giving it a like. Happy studying.